The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
I'd like to introduce Dennis Beaupre. He will be speaking on another means of measuring concrete rheology inside a ready-mix drum. Dennis is director of IBB Rheology in Quebec City in Canada. He formerly worked as an associate director of Unibeton Ready-Mix in Abu Dhabi for 5 years. He is a past professor of Laval University of Quebec in civil engineering, and he's going to give us a presentation now on a probe that would also go into the system developed by IBB. Dennis?
Thank you. What I want to go through this morning is what is our vision at IBB with this new probe. Thanks for the previous presenter. I'm going to go really quickly on the rheology of concrete. I would present you what is the IBB Probe, what it measures, and then how precise and what's the performance of this device. So basically your vision, first maybe about the system. That probe is just put into the drum of the ready mix. It's very good to control the production, the property during production, but a lot of things happen during transport. Concrete is alive, so it's also good to be able to measure it during transport, and especially just before entering a job site, to check very quickly if your concrete is still meeting the requirements. So basically there is a sensor in the drum and there is a display that shows the measured properties. Our vision is that all new trucks in the near future should have a sensor of some sort, hopefully this one, to assess the property so that there's no need to sample the concrete to do tests. So this rheology of concrete, basically, it's defined by the yield stress and the viscosity. Somewhat the yield stress is related to the slump because it's almost a static test, and the yield is the static part of the concrete behavior. So basically, when you do a 2-point test, you just shake, mix the concrete at different speed, and you measure the stress, or you do the opposite. You apply some stress and you measure the speed. In that case, we just have the drum of the truck turning at 2 different speeds, and then we measure the stress, and then we get these flow curve. And from the curve, you get the viscosity and the yield stress as explained previously. So what the probe gives you is those 2 values. And if you put them on a graph where you have the yield stress as the viscosity, so each position of that, on that graph, reflect the behavior of that concrete. So basically, if you have water, you will have no yield stress and very low viscosity on that graph. And if you have SCC, because this is the topic today, you will have somewhat a high viscosity and not so much yield because you want it to flow. And as for normal concrete, they can be almost anywhere on that graph. Those graphs are interesting because it shows you what happened to the mix behavior when you do something to its composition. If you add water to a mix, then you will reduce the yield and the viscosity. If you add superplasticizer, you will not change much the viscosity, but you will definitely reduce the yield or increase the slump. As we saw on the last presentation also, you can also define what we call a workability box for each application. And basically, if you are within that box or those limits, you meet the requirements. If you are outside the box, then you might have your concrete not performing very well. And obviously, if you have a box, it's better to target the middle position. In the traditional industry, basically you will set two limits for slump. High slump, low slump. This will translate into a low yield, high yield. So basically you try to be in the middle. And in normal concrete, normally we don't specify viscosity. So basically what we have on that graph is two infinite line, which if you are between these two slump or yield limits, then you're okay. Your concrete can be very viscous, but we don't normally specify anything like this. So this explains why some concrete of the same slump, some are pumpable, some are not. Some are just too viscous to be pumped, and basically they would be on this end of the graph. So the viscosity we've seen is very important for SCC to maintain its stability. For pump concrete, if you want to pump 300 meter height, you need to control this. You need to be able to measure it before you can control it. The IBB probe is a sensor that allows to assess some concrete properties, slump temperature, inside the drum of a ready mix, automatically without sampling and on continuous basis. Properly used, it also gives rheological property. What I mean by properly used is basically you have to have some time the drum turn at different speeds, so then you get the two shear measurement or pressure measurement. So basically the probe is put on the hatch of the truck. There is a solar panel that maintains the battery charge so it can work continuously. And there is a display that receives the signal from the probe through a radio signal. This is the one probe inside the drum. So what we measure, the sensor measured the angle of the drum at all time. And with the time you can get the speed. So all those in red are the ones displayed on the and the direction of the drum, if it's positive or negative speed. The load on the probe is measured and it is calculated as a pressure. It's just divided by the area, the projected area of the probe. The rheological property, yield and viscosity are measured if you do the proper two-speed measurement. The voltage of the probe battery is also displayed because it's important to make sure that you get enough power in the probe so it's working. The concrete slump is estimated, so initially we didn't want to do that, but it's such a commodity, the slump, that everybody wants it, so we added it in the end because it's still the most used parameter to describe concrete property. Temperature is measured and displayed. The volume is also estimated by measuring the angle at which the probe comes in contact with the concrete. So the probe is fully calibrated for speed, load, pressure, temperature, and slump at the factory. And if you want the volume, because this is drum, this depends on the geometry and the position of the probe, you need to do a very easy calibration process. This is what the display looks like. It's about as big as a computer screen. You can see it from quite far. So basically you have the speed of the drum. This will flash when you reach a constant speed a constant pressure at different speeds. So it will tell the truck driver that he has acquired the high point or the low point. Then the pressure is displayed as an indication because obviously this will change with the speed of the drum. The yield and the viscosity will be calculated and showed only when we have reached the proper condition. The voltage of the battery always there, and it will flash if it's becoming too low, so you have to maybe connect the probe so it gets charged. The slump will be evaluated, temperature always displayed, and the volume if it's properly calibrated. So basically the system will go to sleep if the drum is not turning to protect the batteries. The probe detects when it's in the concrete, then it measures the temperature, it measures the load. When it has two different points, it will calculate those properties that we are interested in. And the slump now is estimated from the yield stress. Before we were using the pressure at a constant speed, but we find out that if the speed is not exactly what you have calibrated the slump for, it makes a difference. So now we're just using the yield, and hopefully we will get a very precise estimation. It's still very good now, but it will just be better. Calculates the volume if the calibration table is there. And basically all the data are sent from the probe to the display every turn or every 10 seconds. Then you have two options. The display will store information. The first idea was just to show the information so we don't have to do a slump test or other tests, and you can look at the display anytime you want. But people wanted to be able to retrieve the data, so we have made provisions so the data are recorded in the display. So you can connect this display to a GPS so you can get the data in real time, or you can connect your computer from time to time to the display and download the data. Now what we are working on is a system manager. Basically, you will just put a display in the batching room, and then when you load the truck, you will send some information using the radio inside that display to the probe, and when the trucks will come back from the delivery, the aging, the slump at delivery, some information would be sent back automatically, so there's no need to use your computer from time to time to download the data. Things will be done automatically. This is an example of the temperature measurement. In some of the trucks, we put 2 probes to see what kind of variation we get from time to time. So this is just a normal warm summer in Abu Dhabi where concrete temperature goes up. And after 2 hours, we added some water because we did sample that truck from time to time to compare to measure the aging of that mix. So you can see that it's very close from each other. This is the yield stress calculated, again from the 2 probe, one in blue, one in red. It's very close, so sometimes you don't see the difference between the 2 lines. It's difficult to find a relation that expresses properly the yield slump. So what we're doing now, we have a table where we interpolate between each of the value because it's very difficult to get a function that would, so that's why here we don't know what is the low slump limit for the probe because in UE we don't use very much dry concrete. This was an accident because we let the concrete too long in the truck. But anyway, the probe was developed for the high workability range where we do use that concrete for pumping and SCC. But it's still working at, we don't know the limit at this time, but the probe can go up to 60. So basically from there, maybe something like 20. We will find out, I guess. If you look at the result for a 2-point test, we have defined for that time that our high speed is 5 RPM for the drum, and then there's a few measurement for each turn, and this is the low measurement. What is interesting is any of those 2 points, this one and this one, will give a fair indication of the property. But it's better to take an average of 2-3 measurement at high speed and 2-3 measurement at low speed. So you average the speed and the pressure for each of those 2 ranges, and then you can make your regression. So the probe will give you here the slope, which is the viscosity, and then the yield, which is in that case 0.14. This is a SCC mix or a very fluid mix that we just let aging for a few hours. And then on regular basis, we took some sample, we measured the spread and then the slump. And the difference between the dot line, actually these lines are made from the equation here. So each of those dots are not a measurement, but just a calculation from the equation you get from but normally you would just get these 2 values from the probe. You have to download the data to look at this. And basically, you can see that the 2 probe, the solid and the dot line for each of the measurement, are very close to each other. So it gives an indication how precise the measurements are from turn to turn. The slump, because everybody is interested in the slump, we asked one technician to just do a few tests, measure the pressure at 1.5 RPM, and then measure the slump. Then we use that calibration, we put it in some probe, and we send those probes to different person in different country. And basically, they came back with the result. We don't know what concrete they have used, if it's 10 mm aggregate, 40 mm, if it says with silica film, or what is the water symmetry show. But basically, you expect the manual slump to match the IBB Probe system. There is a good match, but it's quite a spread, and we tried to find out why was that. So what we did, we tried to understand what could make a difference. So basically, it could be the precision of the test itself, the slump test, as you can do it manually from time to time, even with the same concrete. You will have variation. The probe itself can be precise or not precise. The calibration between the probe and the slump can also be questioned sometimes. And also the operational mode. In that case for the probe, if you calibrate your slump by measuring the pressure at a given speed, then if you don't use the exact same speed to measure, you will have some operational mistake. The best way to evaluate this is to calculate the coefficient of variation of those parameters, and that's what we have done. So basically we take 12 concrete mix, 2 truckload, which we add water and mixer, sometimes just dry powder, so we trick the technician. They think it's always going to be more fluid, but suddenly it becomes stiffer. And 5 technicians took sample at the same time from the truck, and then we send them away so they don't see each other, and then they measure the slump. And on that truck there was 2 probe again, so we were able to see the variation from one probe to the other. So this is the slump measurement from the 12 mix from the same 5 technician. One time according to ASTM, another time according to BS. They did the same test, it's just where you measure the slump that changed. And this is the measurement from the probe on the 12 mix. And basically, if you do the standard deviation, the average of all those results, and you try to calculate to see what's variable and what's not. So for each mix, we calculate the average of the 5 slump, the standard deviation, and then the coefficient of variation. Then we average all the coefficient of variation to get estimation of the precision of the slump test. So in case of ASTM and BS, it's about 8, and for the probe it was about 2. So obviously the probe is a little bit more sensitive than the slump test. Not very surprising. You can also look if you download the data from any mix. So you will have here the date and the time, then the temperature of the concrete, the speed of the drum. And what we want to look at is how the pressure varies from turn to turn. This is every 45 seconds. And what you expect in a normal mix is that the pressure will go up because the slump will go down with time. So you can appreciate here that it's going up slowly. And if you look at many results like this, you will see that the precision from turn to turn is about 1% at most. In that case here, from this turn to this turn, you have 0.02 out of 2.7, so it's about 1%. But normally it will go by 1 digit. When we put this last 12 mix on this previous calibration, this calibration, as I mentioned, was done with not with the yield, but with the pressure at 1.5 RPM. It's a little better when you average the slump because then you don't have too much mistake on the manual slump. We have to assume that this scale is a little bit more precise than this one from the result we just saw. So if you had to make a box of the error on each of the measurements, basically you will have a rectangle which will be 3 times wider than its height. As I mentioned, the first display of the first probe that were installed when they did this initial testing, they were in the cab of the truck. So because the driver was not able to see the speed, I think there was a lot of mistake due to the speed of the drum itself. Now what we're doing, we're using the yield to estimate the slump, and it gives a very much, so there's no influence on the speed of the drum if it's not exactly 1.5. The new software now use this concept. Just a mention about the wear. Some of those probes has been in the truck for more than a year now, and we have measured some of the wear. It is made of stainless, so it's very abrasion resistant. And we estimate that the life of the sleeve here will be about 30 to 50,000 cubic meter. Those measurements were done with crush aggregate, so we suspect that with round aggregate it will be a little bit more. Conclusion. So after 3 years of development and many versions of the probe, the system is a good tool to evaluate automatically, continuously, the fresh property inside a ready-mix truck. The system is easy to install. You just need a welder and about an hour to install it. Give direct measurement and does not depend on the amount of concrete inside the truck. There are other systems that measure hydraulic pressure to turn the drum, but obviously the calibration needs to be adjusted for the quantity of concrete inside the drum. I've been told that it doesn't vary so much with the quantity of concrete inside the drum, but I think you still have to take care of it. It's a good thing to install on all new trucks. Thank you for your attention.
A question to the last speaker. Would you be able to eventually also test or give data with your probe about the setting time of the fresh concrete?
Well, I guess if you leave the concrete inside the drum, you will see a raise in temperature when the sets start to pick up. So I guess by measuring the temperature, you will see. You will also see a big increase in yield stress when the setting comes in. But it's a continuous process. The setting is not a very defined point in time. We have defined it with the penetration resistance, the standard test, but the settings start, when the cement touch the concrete. There is a progressive build up with time. And this is what you see when you see the pressure going up turn from turn. But when do you define the setting itself? It's a continuous process to me, but you will see a raise in temperature as the hydration kicks on.
I got you. It's a continuous thing, but it might be one very important parameter to come to a equation to get the pressure of the SCC concrete on the formwork, how the pressure will be developed. And I think the setting time, I'm coming from Germany, as we are using in Europe, is very important. And I think Lloyd is looking for something like this too. So it's really important for the contractor.
Yeah, I understand. But as a concrete producer, I would be very reluctant to just keep the concrete in the drum until I measure the setting time, because it's obviously a big cleanup problem.
In the real world, when you're using this is something being used after the check that this would be good for the litigation, really, rather than correctly measured right there. When the driver is behind the wheel and taking the concrete there, then...
You see, I delete one slide yesterday, which was why you should use that system, because this will be the subject of a full presentation. But it's not only for litigation, because one of the main reasons we developed it, in Unibeton, in United Arab Emirates, where I've been working for a long time, we have made about 500,000 cubic meter of SCC. And if we had the system at the time, we have the system for 3 years now, but unlimited number of trucks, and we've been developing the new model. But one of the biggest interests in SCC is that just before you enter the site, you know if your concrete is okay. If it's not, you can add the 1 or 2 liter of admixture that you need for the full truck to bring it back to the right spread. And there you don't have rejection. There are people who wants to use this system because in Australia, for example, they have to send a truck 6 hours out. They use dry batch, then they mix it. But every time they have to send a technician for one truck. So if they can convince their client that they have the technician now in the truck, they don't send. So there are some economy. Do you have some QC benefit? There is some production speed up process. There's so many. It's like I always make the analogy of a gas tank. We all have a sensor in the gas tank. And the first time somebody put a sensor on his tank, he probably didn't trust it. So he used a stick to get into the tank and check. And after a while, he understood that what the sensor shows and what the stick shows are matching. So he came to a point where he trusts the stick. But now, and this is what's going to happen, I think, people will develop application like they have for the gas tank, Somebody clever at some point decided to make a light pops up when the tank is low. So if you don't look at the gauge, at least they try to warn you that your tank is low. And somebody else calculate how much kilometer you can drive before you get out of gas. So I think these applications will come, and they're only possible because the sensor exists. Now I think we have a good sensor. I'm sure people will develop application, for end of mixing time, volume. Some people already adjust the mix automatically in the drum. So this is maybe a good sensor to do this. Some other people, I understand for precast operation, what Mr. Nilsson showed is perfect because if you adjust it in the mix, you're going to place it within 5 minutes, so it's perfect. But if you have to deliver concrete 2 hour, 30 minutes, and sometimes you don't know if it's 30 hour or 30 minutes or 2 hours. So this is something you need to follow also. And we're all lazy. We don't like to get our hand dirty doing slump tests. And sometimes you just cannot do it because what you do with the leftover. In Abu Dhabi, we get a price for this because if every truck would have it, we will save 5,000 cubic meter of concrete that is used to do slump tests that goes to the trash every month. So 5,000 cubic meter every month. You can build a tower with this. So there are many applications. We don't know all of them. But I think this was the first step, is to have the sensor that is robust enough to be in a drum of a ready mix, which is a very tough place. But it's also very sensitive, so you can get precise measurement. Mr. Nielsen did it for the mixer, and I met him about 6 years ago in Boma, and I was making rheometer 20 years ago, and then the idea said, okay, but what about my trucks? I need to know in the truck also. So we developed it for that.
Okay, just one more question was, how does it perform under adverse climates such as minus 30 and minus 20 degrees and that? Is it?
So far we have used it in the Middle East, so there's no minus 30. But as a Canadian, we've just put the first probe in Canada about last week. And there is a provision into the electronic board to put a small resistance to heat up to keep the battery. Theoretically, this system should work at minus 20. No problem. But it's very rare you supply concrete at minus 20. Normally you will keep your truck and your aggregate in a heated place and then you will make it. So I don't see a problem if you take care of the truck, but we have put provision. If you connect your probe overnight, it will keep hot. So when you want to use it, it will be ready for using. Yeah.
Okay, because I'm from northern Canada, so. Good.
At ready mix producer, I think it's rather important. When does the system monitor the amount of water added and when?
We don't. This system is just there to assess the concrete property inside the truck. We don't have any gauge or valve on the water tank or in the end mixture tank. But if you add water or if you add end mixture, you will definitely see it because you will change the concrete property. But I will be able to tell you somebody add water, somebody add admixture because it will produce different change. Water will change viscosity and yield and admixture will most likely just change the yield. But I can tell you that something happened. But this was not designed for that purpose, okay? There are other systems. But it's not my goal to do this. My goal was to have a sensor, and I will let the other worry about the application. We are developing this manager, but it's just to make it user-friendly, not to build up more functionality at this time. It's just we want to have automatically the data downloaded. That's it.
Good morning. I was wondering, after you installed the probe, does it require any maintenance, continuously?
So far, we had the last model for 9 months in the ready mix, and there's no maintenance. We had one time to remove the cover, give one hammer bag on the probe because there was some concrete stick to it. Normally, because there's no corrosion, the concrete doesn't stick to the probe. And if it does, this is a very tough place. I don't want you to spend any minute into a drum of a ready mix, but there's a lot of abrasion and it will be worn out. The probe stay clean as I showed the picture. Every time we look inside, this is one picture. I had one at the beginning. It almost looked like this. You can just take a towel and just wipe it up and it's clean. So, of course, if you have half a cubic meter of concrete and you let the probe at the bottom, it would be stuck in concrete and then obviously it will not work very well except for the temperature. But we just recommend that after washing you keep the probe on the high position. So the solar panel would be there and the probe will stay clean.